While operating the furnaces in the shift, it is always a million-dollar question that our shift accomplished comfortably or not, or consistently stably or not. Do you know that what exactly handle our comfort zone? This is basically a cohesive zone of the furnace. This is, and which controls our forecast of our comfort zone, especially about the furnace steadiness. So, this cohesive zone understanding we have to look into in context of the flame temperature. So, what we call it raft. So, this semi-molten spongy layer of partially reduced ore and coke hanging just above the tuer. So it is like a, some softening liquidous band floating bridge inside the furnace. Not solid, not liquid, but alive. So the raft control everything: gas flow, burden descent, even the temperature of your hot metal. So if it is too thick, you get hanging and channeling. If it is too thin, you flood the hearth. So in this session, we are going to pull back the curtain. You will learn how to see the raft with your instrument, how to design it, and how to keep it stable. So question arises that why raft design uh, it's mix or breaks our operation. It is so important. So look at the left side, stable raft. So gas flow evenly through the coke window. You get perfect heat transfer and the burden descent like a escalator. So now look at the right, as not escalator either. We should use it as a basically parachute. So now look at the right. What happens when your raft design is sloppy? So gas channels, pressure spikes, and suddenly you are calling the maintenance shift. Why does this matter to you? Because a poorly designed raft directly hit your KPIs. Productivity drop, coke rate goes up, and silicon spike. So you have all seen it. The furnace start breathing, the top gas pressure fluctuate, and you are chasing the temperature all shift. So here is the operational truth. The raft is the biggest lever that you have. A stable raft is equal to less stress, higher production, and quiet control room. An unstable raft is equal to overtime and headaches. So we don't just hope the raft work. We design it shift by shift. So now how we to actually design this raft. This is all about in this slide. So you're not just doing chemistry experiments, you are just turning dial. So let me show. You have a 5 levers. That is the first coke reactivity, your CSR CRI numbers. They dictate how long the coke windows stay open. Low CSR coke crushes, raft turn into a brick wall, you lose permeability. Second, overburden basicity and MgO. If your MgO by alumina ratio drop below zero point 0.4, the slag becomes too viscous. The raft turn into sticky mud. Third, pellet to lump ratio. More pellet give you a tighter raft, sometimes too tight. Fourth, nut coke layer. You think nut coke is just filler. Wrong. Properly layered nut coke creates micro window for the gas. It's like adding ventilation ducts inside the raft. So fifth is the blast condition, oxygen and moisture. This directly change the flame temperature entering the raft. So you adjust oxygen by 1%, the raft melting position moves up and down by half a meter. So every shift you touch at least three of these levers, understand them, and you become the pilot, not the passenger. So coming to the operational scenarios, basically, and troubleshooting. So so theory is nice, that, but let's talk about what you see on your ship. Scenario one: your silicon keeps climbing to point 0.8 and the hot metal is cold. Most guy add more coke. Wrong move. That happens when the raft is too thick. The gas cannot hit the lower zone. What is the fix then? Increase oxygen enrichment to sharpen the flame, or add a thin layer of nut coke to break the rafts choke point. Scenario 2, gas utilization, CO by CO2 ratio. Is it bouncing like a so that's an unstable cohesive zone. The raft is steering and reforming. Check your ballast stop ring angles. You might need to move the O-ring inward by 2 degrees to thicken the intermediate region. So scenario 3, permeability index drop below 24. That's your red alert. The raft is clogging. Immediate action is increase nutcook layer on the next two charges and reduce the pallet ratio by 5%. I've seen this bring the pressure drop from 1.6 bar down to 1.4 something bar in 1 hour. Every problem has got a raft based solution. Stop guessing, start diagnosing. And definitely, once we act as per those diagnostic, things will work and result will be reflected. So toolkit from blast furnace team. So this is your take home tool, the raft scoreboard. Five things you have checked before every shift hurdle. Number one, 2 year level temperature trend. If it drop more than 30 degrees centigrade in 2 hours, the flame, the raft melting zone is moving down. Bad, raise blast temperature by 15 degrees centigrade. Number two, cohesive zone position. Estimate from shaft probe temperature. Zone too high, increase lumpur. Too low, add nut coke. Number three, permeability factor. You know the formula blast pressure by top pressure divided by your blast volume. So target range is zero point 0.4, 0.48, zero point 0.4 to zero point 0.48. Above 0.48, raft is too thick. Below zero point 0.42, channeling risk. So number four, hearth drainage observation. If slag and iron do not separate cleanly, your raft tripping zone is unstable. Add MGO pallets. Number five, weekly coke layer thickness audit. Use the ballast top data. Coke layer thinner than 250 mm cause raft collapse. I want you to put this scorecard on the control room wall. Every morning mark green, yellow or red for each indicator. When you see yellow, your crew has a plan. Red, call me immediately. Remember, the blast furnace doesn't lie. The raft tells you everything. Your job is to listen and act. Now, if any question or any queries arises, try to diagonalize with your older feedbacks and correlate it properly.